Is there a magnetic fluid? If there is such a thing, how does it behave? Greetings, fluid mechanics enthusiast. Engineer Liu here. On this video, we'll talk a little bit about Magnetohydrodynamics, or MHD for short. Wait, what the heck is that? As Davidson said on his book, which is called An Introduction to Magnetohydrodynamics, magnetic fields influence many natural and man-made flows. They are routinely used in industry to heat, pump, steer, and levitate liquid metals. There is a terrestrial magnetic field which is maintained by fluid motion in the Earth's core. The solar magnetic field which generates sunspots and solar flares, and the galactic magnetic field which is thought to influence the formation of stars from interstellar clouds. The study of these flows is called Magnetohydrodynamics, MHD. Well, before we continue, keep in mind that MHD is a very complex and vast subject that covers phenomena like MHD turbulence. If you think incompressible fluid turbulence is complex, well, you can imagine how MHD turbulence is very much more complex. This video only aims to show you the basic equations behind it. Other topics regarding MHD we will cover in future videos, so be sure to subscribe to this channel for not missing it. Well, continuing, Magnetohydrodynamics, or MHD for short, studies the movement of magnetic fluids, to put it simply. It is a coupling between the Maxwell and Navier-Stokes equations, basically. So, if you're not familiar with the Maxwell's equations, we'll summarize it briefly. They are a set of four equations that describes the laws of electromagnetism, which consists of, first, Gauss' law of electrostatics, which describes how charges create electric fields. Okay, so here we have the divergence of the electric field vector, which is the letter E. This is equal to the charge density, which is here rho sub c, rho c. This is not the same density as we are usually dealing with fluids, is the charge density. So this is a constant which has the units of coulombs per meter cube, okay? And we have this constant of proportionality, which is the permittivity of free space, okay? So the second law of Maxwell is the Gauss's law for magnetism, which states that there isn't magnetic monopoles. So again, is the divergence of the another vector, on this case the B vector, which stands for the magnetic field. Okay, so if you recall that equation from the continuity equation from incompressible fluid flow, here we have, instead of B, we have the velocity vector. So it is basically a continuity equation for the magnetic field. Okay, the third equation, which is the Faradays law, states that time-changing magnetic fields create electric fields. So here we have the time derivative of a magnetic field, and here we have the minus, which states that it will be on the opposite direction, and create an electric field which tends to be like a very similar to a vorticity that happens in fluid mechanics. Okay, so this is the curl of the E vector, right? And finally we have the fourth equation, which is the Paramaxflow law, which states that time-changing electric fields and electric currents create magnetic fields. Okay, so we have here two terms that create magnetic fields. Here is the current density, which is given by this vector J multiplied by the magnetic permittivity of free space. And here we have a term which is divided by this constant c, which stands for the speed of light, and the time derivative of the electric field. So by analyzing this equation, this four set of equations, you can show that they are capable of generating electromagnetic waves that are oscillations in space and time of electric and magnetic fields, and that light is in fact a type of electromagnetic wave, right? So together, this set of equations is capable of describing electromagnetic phenomena and waves such as light and many others. Well, now we talked about the Maxwell equations, let's talk about the Navier-Stokes equations. Well, if you're not familiar with this channel, well, here we talk about a lot about fluid mechanics and the Navier-Stokes equations. They are a set of equations that describes the movement of an incompressible Newtonian fluid, which is some kind of restrict, but includes a very vast majority of fluids that we deal in everyday life, such as water and air below the speed of sound, the subsonic flow of air. So basically, the Navier-Stokes equations is a sophisticated form of the Newton's second law applied to fluid, and infinitesimal, which means a very small volume of fluid. So it deals with volumetric forces, and they can be adapted to include compressibility, compressive fluids such as air at supersonic speeds, electric conducting fluids such as plasma, and hence we can adapt them to include phenomena such as MHD and Magneto-hydrodynamics. Okay, so here we have the acceleration term, which consists of two terms: the time acceleration of a fluid particle and the convective acceleration, which is the term on the right. And on the left hand side of the equation, here we have also the density, which stands for mass per volume of fluid, kilogram per meter cube. And on the right hand side, we have the pressure force here in the form of compressive force, the viscous forces, viscous stresses on the fluid. They are both surface stresses, surface force, and this F term here, which stands for force, but it is a volumetric force which can include electromagnetic forces such as the Lorentz force we will talk about in the next minutes, and gravity. So these are volumetric forces which acts on the whole volume of this fluid. So along with the continuity equation, which is this equation here, in the form for an incompressible fluid, which basically states that mass is conserved. Note that this equation is very similar to Gauss' law for magnetism. This set of equations form a closed set, so knowing the boundary and initial conditions, we can obtain the evolution of a certain fluid flow over time. Okay. So to describe magnetic fluids, which is the objective of MHD, the Maxwell's equations, they can be coupled with the Navier-Stokes equations to account for the Lorentz force. So what is the Lorentz force? Well, the Lorentz force describes both the effect of an electric and magnetic field on a charged medium. Okay, so here basically it has two terms: the Coulomb force, which most of you, if you recall physics from college physics, it's a Coulomb force, the force due to electrostatics. And here we have the magnetic force. So we have a moving charge in a magnetic field. It will generate a force. It's the classical experiment between two rods conducting electricity. They tend to attract each other. So which gives rise to the Biot-Savart law. So this equation here, it's on its it is not on its volumetric form. We will have to adapt. So we divide this whole equation by a very small volume V0. So which basically what we are doing here is the same assumption behind the Navier-Stokes equation, which is the continuum hypothesis, that which is a subject for another video concerning fluid mechanics. Okay, so by applying the continuum hypothesis here, we arrive at the Lorentz force on its volumetric form. Here again we have the charge density rho c, and the first term, the term due to electric force, and the second term here we have the charge density multiplying the velocity of this moving charge. And here is a definition of charge density, or we can call a volumetric charge. So we have a unit of Coulomb per meter cube. Okay, so recalling some concepts from electromagnetism, we have this electric current density, which is a vector, which can be written as this letter J here, which is the charge density multiplying the velocity of the moving charge. So substituting this on the Lorentz force per unit, we arrive at this expression here. So we have this cross product of J and B. So it's another form of writing the Lorentz force per unit volume. So we want to arrive at the simplest form of MHD. So we will look at ideal MHD. Okay, I will talk about this in a few minutes. So it will give us the simplest form of the governing equations for MHD. So several assumptions are made. So we will not get here in full detail of these assumptions. Again, this is a very complex topic, so I'm trying to simplify things for a beginner or enthusiast, or someone who's beginning to study this topic. But one of these assumptions is there are no significant external electric fields, so the Lorentz force is actually simplified to just the magnetic force here. So this term containing the electric field disappears, and we are only left with J cross product B. Okay, so this is our volumetric force, which will act on our magnetic fluid. So now we can finally couple the Navier-Stokes equations with the Lorentz force and the other Maxwell's equations. So substituting the volumetric force term by the Lorentz force, which is this F term here, we arrive at this expression, which is Navier-Stokes equations plus J cross B. Okay, well, we can add other volumetric forces if we want, like I said earlier, gravity, the gravity acceleration, that will be the rho times G the gravity acceleration vector, and rho the fluid density. So one important thing to note here and to be remarked is about the velocity which gives rise to the Lorentz force. So we can, to make sure that we aren't making any misconceptions here. Someone may argue, well, are this velocity, the fluid velocity and the velocity that appears on the charge density here, are the same velocity? Well, in fact, yes. So this velocity, which gives rise to the Lorentz force, in this case it is simplified to the magnetic force, since there are no external electric fields. Well, this velocity happens to be the same velocity of the fluid. Hence, we get a phenomenon which is called the freezing together of the fluid and magnetic fluid. So roughly, this means that the fluid carries away the magnetic field lines of induction. So it's like they are, as I said, freeze together. They are coupled. The magnetic field, induction lines, and the fluid. So this is in fact the same velocity here and on the Navier-Stokes equations and on the electric current density. So continuing the derivation of the equations of ideal MHD, we can substitute the electric current density using the Ampere-Maxwell law. So here we have the curl of B, the magnetic field, which is equal to J plus the varying in time, the time derivative of the electric field. So remember, we don't have any external magnetic fields that can be appreciated on this case. So here we are only left with the curl of B, which is equal to J, in this case the electric current density. Okay, so we can divide out this equation by the constant of which is the vacuum permittivity, magnetic permittivity of free space. So we can now substitute this expression on the Navier-Stokes equations, which are we working on, and we arrive at this expression here. We have the curl of B and cross with B. Okay, so we have two cross products here. So in ideal MHD, as its name suggests, we deal with ideal fluids, so no viscosity. Hence we can neglect the viscous term, and we'll see why we can do that for certain conditions in another video. Okay, so we are left with this expression here, so we drop this term due to viscosity out, and we are almost getting to the equation we are looking for. Well, using some identities from vector calculus, we can rewrite the magnetic force term as follows. Okay, so we separate this expression here, which has two cross products, and we arrive at these two terms here. So rearranging a little bit the equation, we get that these terms that groups together with the pressure, which is in fact a certain type of pressure that appears in Magneto-hydrodynamics MHD, and this other term here. So as I said, this term here is known as magnetic pressure and relates to the pressure of the fluid itself. It acts as another pressure, another force of pressure. It is here it is square, so it is not a vector anymore, it's a scalar. And here we have the magnetic tension. So the Lorentz force, the magnetic force on a magnetic fluid, gives rise to two types of force: a magnetic pressure and a magnetic tension. Okay, so there are various limitations to these equations, despite they can be applied to very a wide range of problems. So, but basically they can be used to describe the movement of plasmas, which is ionized gases basically, which are capable of conducting electricity under certain conditions, which I will not get into here. There are several assumptions to be made. I believe a plasma physicist is capable of explaining and describing plasmas way better than me. Well, besides other types of magnetic fluids. Okay, so hope you enjoyed this brief introduction to MHD. Don't forget to like, subscribe and comment. Share this video with others. See you on the next video. Bye.